Today, on How It's Made. Swords. Pontoons. Grandfather clocks. And fuses. For thousands of years, wars were won and lost by the sword. Swords helped shape history. Today, modern artisans craft historical replicas of these age-old weapons, and they go to the hilt to make sure the details are just right. This reproduction of a medieval sword harkens back to the days of knights in shining armor. The first step to making a sword is to place a piece of high-carbon steel in a fixture. Computer-guided blades carve out the basic shape of the sword with all the specifications of the original. Centuries ago, a blacksmith would have done this painstaking job by hand, but this machine is much faster and creates a much more consistent cut. After about an hour of carving, a nicely tapered sword blank emerges. The blank is submerged in hot liquid salt, a critical step that softens the steel to eliminate stresses created by the carving. Next, the blade is plunged into cool liquid in a process called quenching. It immediately hardens the edges of the sword, but the center cools more slowly. This allows the sword to retain flexibility, giving the blade a springy quality. Using a belt grinder, sword makers fine-tune the blade's shape and hone its edges. The blade is now incredibly sharp. To test its strength, they strike a metal barrel with it. Incredibly, the sword doesn't chip. Next, wax is pumped into molds to make historically accurate copies of the hilt parts, like the pommel, which is the counterweight at the end of the hilt, and the guard that separates the blade from the handle. These wax copies are used to cast the parts in metal. Then the cast metal pieces are smoothed and polished. They smooth away the rough edges on this sword guard and hone its profile. Grinding the pommel is a challenge because it has so many curves and angles. One mistake and the pommel could end up lopsided, which means it wouldn't be very effective as a counterweight. With the blade in a padded vise, the guard slides onto the tang, where it's cushioned with a piece of plastic and a metal pipe. Then, a sledgehammer pounds it into position. Next, the pommel is hammered into place. And finally, a small piece of steel called a peen block is slipped on. Heat from a torch softens the peen, so it spreads as it's hammered down. Epoxy gets a quick stir, then it's applied to two wooden grips as well as to the handle of the sword. Then the grips are clamped into place. Next, black dye is brushed onto a thin piece of leather. The other side is coated with glue. This glue and dye-drenched leather is then wrapped around the wooden handle. It's bound with cord to compress the leather wrap while it dries. Now it's time to brand the blade with the maker's insignia. Chemicals etch the mark into the steel 4/100th of an inch deep. And now you have a replica that's true to the medieval original. A piece of art that takes you back in time at sword point. Coming up, putting together the pieces of a pontoon boat. Party barge, floating bridge, luxury raft. Just some of the many functions of pontoon boats. While their basic design hasn't changed much over the years, new materials have made pontoons bigger, sleeker, sturdier, and faster. And what better way to enjoy an afternoon than on the lake? In the old days, pontoons floated atop 45-gallon steel drums. Today, they ride on custom-built floating chambers made of special aluminum alloy. These floating chambers start off as sheets of aluminum. This rolling machine forms them into tubes, applying pressure equivalent to the weight of 26 elephants. A worker slides each cylinder onto a track to stabilize it for welding. A pacing machine regulates the speed of the welding torch so that it connects the tube's edges evenly, producing a solid watertight seal. Meanwhile, this rolling machine shapes aluminum sheets into tapered cylinders called nose cones. By varying the hydraulic pressure, the operator is able to mold the aluminum into the shape of a large cone. They use a special aluminum alloy to make the chambers shockproof. Next step, making this pontoon leak-proof. First, the welder clamps the nose cone seams together to prepare for welding. Because of its unique shape, the nose cone has to be welded completely by hand. This type of welding, called TIG welding, generates temperatures that can reach 9,000 degrees Fahrenheit. The nose cones will sit at the bow of the boat in front of the other floating chambers. The waffled component at the end of each chamber is called a baffle. It adds extra protection against leaks. This hydraulic press squeezes the sections together for an extra snug fit. Chambers are welded together to form floats. The number of chambers per float varies depending on the pontoon's length. These risers will hold the pontoon's floor in place. Each chamber floats on its own, so even with several punctures, the boat would stay afloat. A worker shoots compressed air into each chamber to check for leaks. He coats the welds with a soapy solution, which will bubble up in the case of an air leak. This demonstration shows that if air can get out through this tiny hole, then water can get in through it. Workers install aluminum cross members to support all the weight that will be added on top. A pneumatic torque wrench is used to bolt the cross members into the risers with rust-proof nuts. Next, the boat's floor is constructed from sheets of pressure-treated plywood. Pop rivets anchor it securely to the cross members. Workers custom cut and glue down a marine carpet. It's made of plastic, so even with a lot of water exposure, it still won't rot. Now for some fade-resistant decals. Rollers crimp the boat's aluminum side panels to make them stronger. Corrugated panels don't warp or wobble as much as flat ones. Using a pop rivet gun, a worker fastens the panels onto the railing. This shaping machine curves the railing in all the right places, bending the malleable metal with varying pressure. Next, workers bring the assembled pieces to the platform. Screws and bolts secure everything to the boat's floor, including the furniture. The pontoon's captain will command the craft using this console. The buttons for the horn, lights, and music sit at the top of the console for easy access. Extra touches bring some of the comforts of home to this craft. Wires and control cables connect the captain's console to this 50 horsepower motor. It's by no means a high-speed engine, but it gives a pontoon boat all the power it needs for a leisurely spin on the lake. When we return, clocking in at a factory where time is money. Invented centuries ago, grandfather clocks run on gravity. When you wind the clock, weights inside are drawn upwards. Gravity then pulls the weights down gradually, unwinding the cables and turning the hands of the clock. The proper term for this type of timepiece is a long case clock. The nickname grandfather clock came from a popular song from the 1800s. This long-established company makes its clock cases out of quality hardwoods, such as maple and oak. To construct frames for the four sides and door, workers fit dowels into holes, then secure the pieces together with screws and glue. They lay each frame in this curing machine that uses high-frequency radio waves to generate heat, drying the glue in seconds. Workers connect the four frames with screws and glue. They'll later attach the door frame with hinges. The next step is to assemble a base, again with dowels, glue, and screws. Once the glue is dry, the assembled frame goes into the base. Now for some embellishment. Computer-guided routers carve elegant wood moldings that give this particular model a traditional feel. Today's grandfather clocks come in styles to suit any decor. Workers carefully sand every single piece of wood in the clock case. The surface must be flawlessly smooth for it to absorb color evenly. The moldings are attached with a combination of glue and nails. These long pieces of wood become curved fluted moldings. They adorn the side of the door frame. This model also features a pair of stately columns above and below the flutes. A worker first positions them with glue, then screws them securely into the frame from behind. The next step is to stain the wood, hand rubbing it to bring out the grain. A coat of lacquer protects the wood and gives it a degree of sheen, from matte to glossy, depending on the model. After installing the glass and door, it's time to install the clock's components. Workers start with long metal bars called chime rods, 8 to 12 of them depending on the model. Each chime rod produces a certain different musical note when struck. Next comes a mechanism called the movement. It contains time-keeping components that trigger the chime hammers to hit the chime rods on the hour, half hour, or quarter hour. This company uses only top-quality all-brass movements imported from Germany. The chime hammers are also made of brass, but they have plastic tips, so you only hear the musical note, not the sound of metal striking metal. These brass pulleys hang from cables connected to the movement. The pulleys will support the clock's 3 weights. After connecting the movement to the clock dial, a worker inserts a decorative detail, a wood panel to frame the dial. Then she installs the clock's second hand into the center of a miniature dial. On the main dial, the hour and the minute hands are attached. Depending on the model, these aluminum hands are painted either black or gold. A decorative nut secures them. Finally, the all-important weights and pendulum. The weights are brass canisters filled with lead. Each one weighs almost 9 pounds. The pendulum sways from side to side at an even pace. This ensures that the clock keeps accurate time. It also drives the clock to chime on the hour or fraction of the hour. All you have to do to keep this clock ticking is wind it up about once a week. Up next, behind the scenes at a fuse factory. Invented in the 19th century, fuses are designed to blow whenever there's a power overload. This stops the flow of electricity and prevents a wiring fire. We may never see fuses in action, but they're constantly working to protect us wherever electrical current flows. Choosing the right fuse depends on the amount of current. To make a high-voltage fuse for use in electrical substations, this machine cuts notches into a long silver strip which will serve as the fuse's element. The notches will help control the way the fuse blows. Bits of soft metal are melted onto the strip. These will be the points where the fuse blows. One end of the silver element is welded to the top of a ceramic core, and the element is wound around it. Workers slide the element core into the fuse casing and bend back metal tabs. Then, using a soldering technique called brazing, they seal everything together. They take a brass washer and wind ignition wire around it. They're assembling the striker pin, the device that indicates a blown fuse and shuts down the power. The striker pin is fitted to the washer, and with the wire protruding, it's placed into a holding device. Explosive powder is added to each striker pin. Then the bottom of the pin is plugged with a rubber stopper. Next, the striker pin is pressed into a brass capsule. This will contain the mini explosion that pushes out the pin when the fuse is blown. This test run shows how it all happens. The pin's ignition wire is wrapped around an electrical post. Workers clamp down the pin and position the pendulum that swings to indicate the amount of force with which the pin fires. A jolt of power detonates the explosive. This causes the pin to protrude, signifying a blown fuse. Now, a metal eyelet slides onto the striker pin's ignition wire, and then a wire coil is attached to it, completing the striker pin's ignition system. A snare pulls the whole assembly into the fuse. The end of the coil is tied to the fuse's cap. And an outer cap is press-fitted over the inner one. Next, the fuse is filled with sand. This sand will absorb energy from the element when the fuse blows. Automated rods tap the fuses to compact the sand inside. Next, an outer cap is lubricated. And it's pressed onto the other end of the fuse. This machine spins grooves onto the cap, pinching it tightly to the fuse casing. A current is run through each one of these fuses, checking the voltage to confirm that they're in good working order. Sealant is then pumped around the cap's rims to make them completely airtight. Finally, the safety information is affixed to the fuse. And some electrical specifications are stamped onto the caps. Now, these fuses are ready to go with the electrical flow and blow at the first sign of trouble. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.